My name is Raoul van Loon. I'm a senior lecturer in the School of Engineering, and I am part of the Civil and Computational Centre. I would call myself a Computational Biomedical Engineer, which essentially means that we want to use mechanics and fluid dynamics to understand the human body. So like an aerospace engineer would study the flow around wings, we want to study blood flow through the arteries. And like a civil engineer wants to study the mechanics and the strength of a building, we want to assess basically the strength of arterial structures or heart valves and structures like that. So I work mainly together with engineers, bioengineers as well, like myself, and one computer scientist. The area I work in is very multidisciplinary, and therefore there's a lot of opportunities and directions in which the research could go. A good example is patient-specific modeling, where we take a scan, a CT scan or an MRI scan that has been done in the hospital, and we extract the geometry from that. And what we can do is do a fluid dynamics study or a mechanics study on those structures which are specific for that patient. So one of the areas, one of the arterial structures that we've been focusing on is the carotid. The carotid runs in the neck of the human body, and it's an artery that splits in two. And this is a common area for plaque to build up. And these plaques can rupture or they can occlude the entire artery, which will cause strokes. So what we are trying to do is to assess how the fluid dynamics and the mechanics and the interactions between the blood and the walls, how they link in with the biology and the progression of a plaque and the formation of a plaque. So we can use these studies to understand disease better and to come up with new, more advanced diagnostic criteria. A more recent example is a project that I'm doing in collaboration with Texas A&M and the lymphedema clinic in Singleton Hospital. It focuses on the lymphatic system, which is essentially the system in your body that drains fluids from your tissues. If it wouldn't drain these fluids, it would cause enlarged body parts, which is very uncomfortable and is a chronic disease. If you would have asked me a year ago anything about lymphatics, I wouldn't have known. But it was a professor in Texas who contacted me and said, I know you work on heart valves. Can you do something on lymphatic valves as well? So our research aims to study and analyze the contractility and the pumping function of the lymphatic vessels. And these vessels are as thin as a hair with little valves in them. So if a valve closes, it causes pressures and stresses on the leaflets and may cause the leaflets to fail. So once we understand the lymphatic pumping function better, we can focus on optimizing treatment methods or develop possible new treatment methods. One of the directions I do want to take is to use my models, the mathematical and computational models, to translate them into the clinic, so actually use them in the clinic rather than sit behind my computer and get a better understanding. So for me, engineering can play a very big role in modern medicine and can help to improve clinical care.